Hello class, this is Dr. Amankuna again, and this is the video for section 2.2, the limits of a function. Okay, in this video, these are the line objectives. We'll find one-sided limits of a function, two-sided limits, and then infinite limits of a function. In this way, we will determine the vertical asymptotes. So in other words, as you did in algebra, where you have a rational function and you find the vertical and horizontal asymptotes, we'll be using calculus, which is limits, in this case, to find those and to be able to sketch the graph later on in chapter 4. Okay, so let's consider first the one-sided limits. Okay, what do we mean by that? Now let's consider the function h is a piecewise function. It is 0 when t is less than what? 0, and then it is 1 when t is greater than or equal to what? 0. And so if I draw the graph for that, okay, this will be the graph. Okay, this is x-axis, and that is y-axis. Okay, it is 0. Let me pick a different color so that it is 0 when t is equal to, this is actually t, okay, not x. Okay, it is 0, okay, when it is what, less than that, and it is 1 when the t is what, greater than equal to what, equal to 1. So this is it's not a hole. Okay, there's a hole in what, at 0. So here is not a hole, right? So here is what, t is greater than or equal to 0, and then t is less than what, 0. It's a piecewise function. And so what we say that, how does the t, the function, behave near what, 0? In other words, if you're approaching 0 from the left and approaching it what, from the right. Now remember, from the right, we say that t, symbolically we say this is what, approaching 0 from the left. That's how we write it. And then from the right to is a t approaching what, 0 from what? We put a plus, means that we are considering values greater than 0, but we are getting closer and closer to 0 from the right. Okay, so how does it behave? Okay, this is what is happening, that if t approaches what, 0 from the left, the function is what, 0. And if t approaches what, 0 from the right, which is positive, the function is what? Value is 1. Okay, so this is the what? The limit values. And this is what we call the left, we'll define this later, is the same as the left hand, okay, limit. Okay, and this will be the right hand limit. Okay, let me change my color. Okay, so left hand limit and the right hand limit. Now, in this case, you see that they are not what, equal. And so what you can say is that as the limit, okay, the left hand limit, the limit t approaching 0 from the left of the function h is actually not equal to the limit t approaching 0 from the right of the function t, h of what, h of t. Now, this is what, the left one is 0. We know that 0 is not equal to 1. So how does it behave? Okay, so if you want to consider the limit, so t approaching 0 of the same function, h of t, this actually does not what? Does not exist. That's how we say it. Does not. This means does not exist. Okay, because the one-sided limits are not equal. Okay, so it's important to know that. So we already explained those limitations, okay, so that you could see what is happening there. Now, notation is that when t approaches 0 from the left, we use this symbol for that. T, then the right arrow, and then 0, we put the negative 0 on top of the number. Okay. And then secondly, same as what t approaches that, and that means it indicates that we consider only values of t that are greater than what? 0. The first one, we consider values less than what? 0. Okay. So this is basically one-sided limit. Now let us define this. Generally speaking, that if you have a function, one-sided limit, that x approaches a from the left is equal to what? L is a value. Okay, we say that this is called the left-hand limit, another name for that, or we just say that the right-hand, the left-hand limit, or we can say that as x approaches a from the what? From the left. Okay. So likewise, if you have that definition, you can write the same thing like this one here, but it will be plus. That is when you consider the right-hand limit. Yeah. So similarly, the right-hand limit is given by this, which is right here. Okay, where x is approaching a from what? From the right. This is the right-hand limit for that. Okay. So that's the notation. This means that we consider only, again, x values that are greater than what? A. Now, look at these two diagrams. Okay, we're approaching, x is approaches what? A from the left. Okay, and this one, x is approaches what? A from what? From the right. Okay, now here, this value right here, okay, this value is what? This is L, that's a function value. And over here, this is what? The value is what? It's L. Okay, now if you have these two to be the same, then like we said, as for the previous example, we realized that 0 is not equal to 1. So we couldn't say that as x approaches 0, which would be the definition for a two-sided limit. So in this case, since both of them are L, then we can say that the limit x approaching what? A, without any sign on top of that, of the function f of x is equal to what? L, because, okay, because the left-hand limits are what? Are equal. The right-hand limits and then the left-hand limit, they are what? They are all the same. In other words, the one-sided limits are equal, therefore the limit exists for that particular word, x approaching A. Okay. Now, let's consider this example. Okay. This example is similar to one of the homework problems. That here we are given the graph over here, and we want to find the limit values for the following, that A, B, C, D, E, and then what? F. So we're going to write everything here so that you see why we mean by that. So for A, okay, when you have we'll consider the limits, x approaches 2 from the left of the function g of x. And if I look at the left, this is my 2, this is where the 2 is. Now if I'm approaching 2 from what? From the left, okay, this is the value. And so the function value is what? Is 3. So this is equal to what? Is equal to 3. Now for B, the limit x approaches 2 from the right of the same function. What is it equal to? This one, there's a jump here. This is the value that we are considering. It's the same 2, but we are approaching 2 from the right. And the function value in this case is approaching what? It's approaching 1. So that is equal to 1. Now C, it says that the limit x approaches 2 of the function. Okay, what is it? Okay, this one does not what? Does not exist. Or let's put it this way, D does not exist. Why? Because 1 is not equal to what? 3. Okay? Parts A and B are not the same. This is 3, this is 1. In other words, the left-hand limit is not equal to the right-hand limit. Okay, let's go to a D. D says that what is the limit function value as the x approaches 5 from the left of the same function g of x. Okay, let's go to the graph. This is where the 5 is, and we're approaching this from the left. You go to the graph, this is the, well, it is a hole there, but the function value doesn't exist, but the limit exists, even though there's a hole. Okay, so what is that value? In this case, is equal to what? Is equal to 2. Okay, now E, what is this, the right hand limit as x approaches 5 from the right? X approaches 5 from the right. Okay, now if you look at this, it's the same one. So if you're approaching it from 5 from the right, it's the same what? It's the same value. Now that is also equal to what? Is equal to 2, because you have 1, 2, this is 2. Okay, so do you see that now the question is that what is, this is E, what is F? Okay, what is the function value, the limit value as x approaches 5? Sorry, of g of x. Okay. Okay, now what can you say? Because look at it, the two are the same. Look at it, the left hand limit is equal to 2. The right hand limit is also equal to 2. So the limit as x approaches what? 5 is what? Is 2. Because the limit x approaches, 5, x approaches 5 from the left of the function is equal to the limit x approaches 5 from the right of the same word, the same function. Because you have 2 equal to 2. That is why this is what? This is true. Okay, but notice that what is the function value? What is g of what? G of 5. Okay, what is g of 5? According to diagram, g of 5 is this value here. G of 5 is this value. Because it exists, and that is this value, which is it's actually it's a little over 1. So I can say that this is like maybe 1.2. Okay. Now notice that it is not equal to 2. This is not the same as that. It's important to know that. Now, very soon when we get to chapter section 2.5, we'll talk about continuity. And so for continuity, we're going to use the limits and we will consider the function value. So in this case, suppose that the function value at 5 is also equal to 2. Then we'll say that the function is continuous at 5. Okay, so that is just something you should bear in mind. We'll get back to it when we get to section 2.5. Okay, so then we have actually defined a two-sided limit. Okay, when you say the two-sided limit, we just want to say that in this case, a two-sided example of that is the F. Okay, it's this part, the F, and then also the C. We're talking about the F and then the C. This is what we call the two-sided one limits. Now, as you can see, can deduce from these two examples, if the one-sided limits are equal, then the two-sided limit will exist and is equal to the same value. It's a rule. Okay, so the two-sided limit is defined. We're going to investigate this using algebra. Example, specific example. So let's say that our function is f of x is equal to x minus 2 divided by x squared plus what? Plus 4. Okay, so we want to know the behavior of this function near what? Near 2. In other words, we want to find what's the limit, okay, x approaching 2 of the function f of x. Okay, this is what we want to determine. Now, in doing so, we need to consider the left-hand limits. We're approaching 2 from the left and also approaching 2 from what? From the right. Now, if these two are equal, then guess what? Then this limit is equal to that value. So suppose if it's equal to L, if this we found this to be L and this is equal to L, then we can say that that is equal to L. So we're going to use a Gauss method, and I also use algebra to show you. Okay, so let's go to a table. So in this table, what I'm doing is that I'm picking X. This is what X is approaching 2 from the left. And this table is what X is approaching 2 from the right. Okay, as you can see. Now, the first value is what? 1.5. Say 1.8. Then we pick what? 1.9. You see that we're approaching 2 from what? So this is like a number line like this. We have 2 here, and we're approaching 2 from this side and from that side. And so I pick 1.5, which is maybe somewhere there. Okay, 1.5, and I pick 1.8, and I'm picking 1.9, getting closer and closer to 2. Now, what I do is that I just take this function. Okay, if I want, I can simplify this function actually. Okay, which I'll come back to later. We have x minus 2 over x squared minus 4. Okay, this is the same as x minus 2. The denominator is a difference of squares, so that's x plus 2 times x minus 2. And of course, this will cancel out. So this will simplify into what? 1 over x plus what? Plus 2. Okay, so let's go back to our table. So what is happening is that if we substitute values, pick values of x closer and closer to 2 from the right, now look at what is converging. It's converging toward a value which is what? 0.25. Then we do the same thing for x approaching what? 2 from the right. What I'm doing is that I pick x is equal to 2.5. I substitute that into the function x minus 2 over x squared minus 4. Or I can use this 1 over x plus what? X plus 2 and then evaluate. So if x is equal to 2.5, then I have, in this case, I have what? 1 over 4.5. And when you evaluate, this is the value that you get. Okay, and then repeat it for each of the values in the what? The first column, the second table. And look at it. Look at these two values. See that they're the same. And so what can you say? That the left-hand limit, x approaching 2 from the left of the function f of x is equal to 0.25. And then also the limit x is approaching 2 from the right of f of x is also 0.25. Therefore, what is the limit? Let me write it up here. What's the limit? X approaching 2. The behavior of the function, in other words, the function value as we are approaching 2 from both ends. Okay, of the function f of x will be what? Which is going to be what? 0.25, which is the same as 1 over what? 1 over 4. Okay, so this is what we mean by what? Finding the limit of a function, which is a two-sided. Okay, very good. Okay, now I can draw a graph of this function, if you remember. Okay, let's draw a graph of this function. Now this function behaves as what? This like this 1 over what? 1 over x. Now 1 over x is this how it behaves. If you remember. Okay. But if you have this, looking at this x plus 2, it's behaving like that, like a 1 over x, but it's a shifted to the left, 2 units. Okay, so there's a vertical asymptote here. So this is 1, this is 2, that is minus 1, minus 2. Okay, so there's a vertical asymptote. The y-axis is shift to what? to the left, 2 units. So this graph is going to behave like that, and going to behave like this. Okay, this is your X, that is your what? Yes, your Y. That is a vertical what asymptote. Okay, doesn't get to it. We make sure I have that correctly drawn. Okay, all right. So here is 1, and here is what? 2. But when X is equal to 0, 2, there is what? There's a hole at 2. Okay. Now, what is happening is that this value right here, okay, that's the value that we got. It is the what? 0.25 or 1 over what? 1 over 4. Okay. So, what is the function value of this? And that is actually the value that what we got. Okay. So from this, if we are approaching X from the, okay, so we have this rule. What we have said that we have this rule. I think I have typed it here. Okay, which is the next one. So by comparing these definitions of one-sided limits and two-sided limits, we can see that we're using that the two-sided limit exists and is equal to L, even only if the left-hand limit and the right-hand limit are both equal. In other words, the two-sided limits exist if and only if the one-sided limit exists and are equal to each other. Okay, so this rule is very, very important. It's a fact and then it's a rule. Okay, so let's consider this diagram. These figures, okay, it shows that the part what? C, okay, the part C, and it's not what defined in what? In part B. Okay, so the function value when Ax is equal to A, it is not defined. It's on the graph, there's a hole there. Okay, and here too there's a hole. But here the f of what? F of 2 of sort of A is equal to L. Over here, f of what? A is not L. It is some value. It's this value right here. So you can call it a C or something. Okay. Over here too, the f of what? F of A is not equal to what? Is not equal to L. However, the function value, okay, the limit value at what? As X approaches A for the function, for each of these is what? Is C, is L. Okay, if you approach it from the left, it's L. If you approach it from the right, it's L. For this one, if you approach it from the right, it is L. If you approach it from the left, it is L. This one to the same. Okay, so in each of these figures, the function, the limit value of the function as X approaches A exists and is equal to what? Is equal to L. Okay. So now, let's take another example. Here you have a function, it's a trig function, tangent of 3x divided by the tan of what? 5x. So I'm going to we're using the guess to find the limit value of the function. We know that when tangent of 0 is what? Is 0. Okay, that is why if I substitute 0 into this would be 0 over 0, which is indeterminate. Excuse me. And therefore, I'm going to use the limiting value as X approaches what? 0. And we consider it from the right and from the left. So what you see here, plus or minus, okay? Okay, yeah. The plus or minus indicates that I'm just picking X, okay? X is approaching, it's less than, sorry, this is supposed to be 0. It's less than or greater than 0. So what you have there is supposed to be X less than 0 or X greater than what? 0. Now, if you consider the plus is greater than 0 and the minus is less than 0. So for example, if x is equal to 0.2, then I have f of 0.2 is equal to the tangent of 3 times 0.2, which is 0.6, divided by tangent of 5 times 0.2, which is what? 1.0. Now, if you evaluate that, that is equal to 0.439279 to 6 decimal places. Okay, so if you also consider x is equal to negative 0.2, it will give you the same value. And that's why I have plus or minus for each of these guys here. Now, what is happening is that it's approaching, what is happening is that the s approaches 0 from the right, okay, of the function, and then x approaching 0 from the left and the right. This value, the function value, is what? Is going towards 0.6 for everything. So symbolically, we will say that the limit x approaches 0 from the left of f of x is equal to 0.6, and then the limit x approaches 0.0 from the right of the same function is also equal to 0.6. Therefore, the limit, the behavior of the function as x near 0 is what? 0.16, because these two values are equal. Okay, and that will be the answer for that. Okay. So now let's talk about our infinite limits. Now, infinite limits, like we said, I mentioned before, we're going to use this to find a vertical asymptotes. That's our third objective for this section. Okay. Now, the intuitive definition of infinite limit basically is that if you have a function and then x is approaching that value, okay, a certain value, and the function does not exist, that means it goes to infinity, either it goes to positive infinity or negative infinity. I believe I have an example like that, okay? Positive infinity and then negative infinity. Then we'll say that, for example, the graph that I showed you, this graph, okay, which is for 1 over x. Now, here you see that the y-axis is your vertical asymptote, okay? X equal to 0 is what? The line x equal to 0 is the vertical asymptote, okay? All right, so we're going to define its definition for that, and we need to know this is what we call the what. If the answer is what doesn't exist, whether it's positive or negative, that's what we call what? Infinite limit. So if you consider this function here, this graph, okay, now this line, look at the line x is equal to what? A. Now as x is approaching, okay, approaching A from the right, and then x is approaching what? A from the left. It goes to what? Positive infinity. Guess it increases indefinitely positively, okay, for this figure. So how do we say that? We say that the limit, okay, x approaches A from the left of this function f of x, it goes to positive infinity, and then the limit x approaches A from the right of the same function, it also goes to positive infinity. So what can you say about the limit of the function as x approaches A? The two-sided limit will also do it because these two are what same. Now, similarly, in the second diagram on your right, the limit x approaches A from the left, okay, of the function, it goes to what? It goes positive infinity, negative infinity. And then the limit x approaches A from the right, sorry, this is the left, okay, of the function. Okay, that's the first one is the right, the left is the right, also goes to what? positive what infinity. And therefore, this is true. Using the rule that if the both one-sided limits are equal, then the two-sided limit is also equal to the same that value. Okay. So this is the definition, formal definition for a vertical asymptote. We can use algebra from Math 126 or Pre-Calc 1 to find vertical asymptotes, but here we're going to use what? Limits or calculus to do the same thing. Okay, so here we can define, when you have this limit, one side also works for the two-sided, it works for the one-sided, the definition is the same. Now, if I find the vertical asymptote, I could use any of these, not all of them, just one of them, any, okay? Any one of them. Okay, if we consider the one-sided limit, if I consider this and I get negative infinity, then I can conclude that it goes to what the line x equal to a is what is a vertical asymptote like that. Okay, so now let me use this piecewise function g of x. Okay, let me draw. I think I have the graph here. Let's draw the graph for this. Draw the graph for this. So you have this. Okay, when it's what? When it approaches 0, it's not equal to 0. Okay, we have this, right? And it said it is 0 when x is equal to 0. So we have this point here. Okay. You have the origin. Let me change the color. Maybe that will help you see. Okay. So what is happening is this. What is the one-sided limits? Let's consider them. Okay. What is the limit? X approaches 0 from the right of the function 1 over x. Or in other words, the g of x in this case. Okay, if approaching it from the right, 0 from the right, it goes toward a positive infinity. Now, if you approach it from the left of the same function, okay, it's equal to negative for infinity. Okay, it goes here, and that one goes up there, like that. Okay, therefore, what can you say? What is the limit? X approaches what? 0 of g of x. This one does not exist. Okay, this means, I mentioned this before, does not exist. Okay, because it's kind of rotating. You're going up, increases positively and decreases negatively, and they are not. There's no way they will be equal. So in this particular example, the what you call one-sided limits are not equal. However, the vertical asymptote, okay, since we got this, we can say that or that, okay, this or that. We can say that the line, okay, x equal to 0 is what? The vertical asymptote. Okay. Now let's consider a last example. Given the function f of x, okay, which is the tangent of what? X. Now we know from trigonometry, tangent of x is sine over what? Over cosine. Okay, so there are potential vertical asymptotes whose cosine, where cosine is what? Is cosine of x is what? 0. Okay, so it means that we will consider x approaching what? 0. We'll check either one-sided limit and see whether plus or minus, see what's happening. Okay, so we'll look at the cosine, the function is approaches positive 0. Okay, as x approaches what? Pi by 2. Remember the period? Okay, I have the diagram, the graph here. So this will help us to explain it better. Now, when cosine is approaching what? approaching 0, okay, from the right, okay, the x approaches pi by 2, okay. So in other words, when x is approaching pi by 2 from the left, that is, you have, sorry, from the right, pi over 2 from the right, as x is approaching this value, okay, the function, the tangent of x approaches what? Positive for infinity. And then as x approaching, okay, pi by 2 from the left, the tangent of x approaches what? Okay, this is, the first one is negative, this is positive for infinity. So it goes up and it goes what? Down like that. So each of these will tell me that the line, okay, x is equal to pi by 2 is what? Is a vertical asymptote in the graph. Okay, and then since pi, what do you call it? Tangent, the period is what? Is pi. We can generally, all the lines, okay, all the lines in the form x is equal to pi by what? 2 plus n pi, where n is what? 0, 1, 2, like that. Then all the integers. This will all be what? 5 plus or minus is an integer. So all these lines are what? Vertical, what? They're all vertical asymptotes. Okay. So to recap, we have considered one-sided limits, two-sided limits, and then we use it to find vertical asymptotes of a function. So that brings us to the end of this section 2.2. Thank you.